rules, just production rules. And why we have that such production rules is basically from a non-terminal to how we derive into a terminal based on the production. So for example, E, if we combine E and ID, how we can produce the ID based on this non-terminal, based on this rule. This rule is just basically telling you from E prime, and it goes to E prime, and etc. to find what exactly how we derive to the terminals. And also we have to talk about this one, and we have to talk about translating the predictive parsing table into actual recursive descendant functions. I think we have to talk about this one. Each non-terminal becomes one function, and each row of the parsing table corresponding to a switch statement inside a function. Okay, so what we have shown here is the T and T prime. The function T handles the terms if the token is identifier or left parenthesis. Left parenthesis, it just simply calls F followed by the T prime, as you can see here, F, T prime, and break. So that is exactly the function. The production rule we have is at T to the FT prime. That's exactly the production rule we are following. And for the function T prime, it manages continuations of a term, which the look ahead is a star symbol or multiply symbol. It consumes that operator and recurs on the T prime, recurs on calling the F, and recurs on the T prime. And again, and everything otherwise, if what we have here is look ahead is a plus symbol or end of file or right parenthesis, will simply do nothing. That is basically mirroring what we have here. Only on the star symbol or multiply symbol, we have the production. Everything else will be the empty string, or the empty set, the epsilon. So this structure just mirrors the grammar directly. So the beauty of this one, we have talked about 3 different ideas. What are they? Modularity is one. Yes. Readability is the one. And lastly, what? Inheritance? Inheritance means what? Extendability. Of course, that's the 3 words I want you to remember for this slide. Why we want to have the non-recursive recursive descendant parsing is basically from these 3 words. Okay, now what we have, you have understand everything, and what you have done in homework 3 is a recursive descendant parsing. Okay, so now what we have built here is what we can do is to build and run a recursive descendant parsers. We can make it more resilient. In LF1 parsing table, a blank entry means no valid production exists for that non-terminal and terminal pair. In a naive parser, which would cause exceptions and stop the analysis immediately, which exactly your homework 3 is doing. And naive but effective. That's a very correct behavior logically, but very unhelpful for the users who need to see all of their syntax mistakes, not just one at a time. Okay, that is the idea of what we have here. We want to make the program's life much easier, not much harder. You don't want to see, okay, we have a syntax error, we want to fix that syntax error, and that's causing a time. Could be a minute, could be two minutes, but you have to compile this program again, which in a larger system could causing an hours or several hours. Then you have to compile this again and see, oh, I have another syntax error. I have to fix it and compile for another 2 hours and then come back to another errors. And that's not good. We want to compile once, given all the errors to the user. And the user knows, oh, I have a lot of errors happening here. I can fix them, all of them. And then coming back to the compilation, then compiles the stuff. It saves a lot of time. So what do we have here? Why we want to do that is we can handle such blanks. So for example, we can just handle what we have the parsing table. Whenever we have a blank cells, it means an error. If you still remember that, that's the exact behavior we're doing. What we are doing here for the error reporting is we can handle that such blanks very gracefully. So what I mean by gracefully is whenever the function T encounters a token that doesn't match to any valid production, means empty cell, it prints the diagnosed message and or like, for example, expected identifier or left parenthesis, and or that can pretend the missing tokens was there. We can continue parsing rather than just stop right there. So this approach is called error recovery by insertion. It doesn't modify the input stream, but lets the parsing continue consistently by inserting or skipping the tokens virtually. And then the compiler collects the multiple syntax error in one pass, making the parser much practical and user-friendly during the debugging. Then here in this slide, we just simply talk about history. So history is part of the learning journey. What we have here is in 1976, what we have is a person whose name is Nicholas Wirth. And that's the creator of Pascal. He proposed a structured approach to error detection and recovery that remains very influential today. So his insight was that every parsing function should know not only which tokens are valid to begin its rules, but also which tokens are valid to follow it. So these are two sets we have studied. First and follow, okay? Allow the parser to decide whether to keep parsing, skip the tokens, or return its control flow back to its caller whenever an error occurs. The flow set in particularly, and it helps the parser resynchronizing by skipping ahead until a safe boundary is found. So Wirth suggested that each parser procedures carry three parameters. Three parameters are listed right here. So just keeping in simple words, the S1 here, S1 is admissible next tokens. Essentially, it's just first set. S2 is stopping synchronizing tokens, stopping or synchronizing tokens. And that is our follow set. S1, first set, S2, follow set. And lastly, we have N. N is the error number used for diagnostic. What we have here in homework 3 is we would have, I think on certain page, we have a whole bunch of a list of errors. They have 1, 2, 3, to 15. You can simply give them an error code. Error 1 is what, error 2 is what, error 3 is what, that will be it. So that is the error code we're talking about in. So this design simply allows the recursive descendant parser to detect the mismatches early and print clear messages and recover smoothly without crashing the entire compilation process. That's the only key takeaway you can have on this slide. So now let's see how the Wirth recovery idea looks in practice using a production rule. What we have here is N to alpha. Now, each non-terminal in alpha or in a recursive descendant parser is implemented as a procedure. We have understanding that each procedure is representing a non-terminal. Here we call N. The code for alpha represents that whatever the sequence of terminals or non-terminals N can expand to. So before we begin parsing alpha, begin with parsing that, we have a couple of rules we need to check. The first one is we need to first check the next token is lying within the first of alpha. So if not, we are going to skip the token until one is being found. So that one is coming from the first of alpha. This prevents the parser from dividing into alpha with an invalid look ahead. Similarly, when we leave in the parser or the procedure N, the next token should belong to follow of N. If it doesn't, we skip the tokens until one from the follow of N appears. So ensuring that when we return back to our caller, the parser is back into a safe and synchronizing state, okay? That's only two things we are doing here. But how we can implement that directly refer to our pseudocode. Pseudocode here is we are doing here. So to implement that logic, we are explicitly checking the procedure in the procedure. So before parsing alpha, we simply call test first of alpha, as you can see here. And again, afterwards, we are going to call test follow of n. So this test function is listed right here. It just plays a both detection and recovery role. It just simply verifies if the next token is in a valid set. If not, it's going to trigger the error and giving the error number and prints a diagnostic. And it repeatedly discard, as you can see here, repeatedly discards the token until a valid one appears. That's how this line is telling you. So this design just simply allows localized repairs without unwinding the whole parsing. So for example, if we are missing let's say a close parenthesis, the test will simply skip irrelevant tokens until one is found and continue. So keeping those keeping the rest of the parsing process intact. So this is a very simple yet remarkable robust idea for compilers that must handle more formed programs gracefully. Okay. Now, after executing the code for alpha, we know that the lookahead may have changed because alpha might include procedural calls and that consume additional tokens. We know that simply because we are processing the alpha into a different, maybe processing into a different non-terminal rules. But for that reason, the procedure n must verify the next token again. So this update algorithm, what we have here is simply call the test with a union first of alpha and the follow of n. Okay. So this union, what is happening to the union? This union ensures that any valid token for continuing alpha or safely exiting n will be accepted. That's the thing. That's the only takeaway from this slide, where we have the union. And if the token is in alpha of A, parsing continues normally. We know that. And otherwise, the parser will skip forward until something from follow of n is seen. So this refinement is basically a refinement, keeps each procedure self-contained and ensures the recursive calls always return the parser to a valid position in token string. Okay. To make the recovery more flexible, we allow each parsing function to accept follow set as a parameter, as you can see here. This way, whenever the procedure n is called, its caller specified what token can legally follow n's derivations. Inside n, we simply call the test with the union first of alpha and the provided first follow set. Okay, so if the lookahead is valid, we are going to parse the alpha normally. Otherwise, we are going to skip the tokens until one of those symbols appear. So by passing the follow sets explicitly, the parser can coordinate with the recovery across multiple levels of recursion. And this design simply helps the parser resume the parsing at the right position in the source code rather than losing track of where it was when the error occurred. So again, coming back to the single key takeaway you could have is we could have specified the follow set here. But why is that? Have you considered why we want to have an argument or parameters in the procedure n? Do you understand the reason behind this? If we are going to have what we have here previously, is extensibility, modularity, and readability, what exactly the rule we are following right here? Extendability? It is not extending a different thing. It's still following what we have from the previous slide, follow of n. More usable? Okay, more usable means what? Modular. It means modularity. Why we have the parameters follow set to be here as a parameter? It means, let me give an example. What we have here study about T prime or T prime, E prime, F prime, etc. Those things, if we are going to have a non-terminal function for that, it means we are going to have what? A dedicated function for T, dedicated function for T prime. That's two functions already. A dedicated function for E, dedicated function for E prime. That's already four functions, which they are doing exactly the same thing in this lecture. Not necessarily related to your homework 3 grammar, but in this lecture, we have four different independent functions defined already. But what we have here, if we have such function exist, we can simply merge those four functions into one function, which is this one. But how is it different? The only difference what we are going to do is once we call that function, we simply given the parameter as follow of E, follow of E prime, follow of T, follow of T prime. That's the only thing we're going to. It's only the calling instruction to be different. But what we are saving here is size of the file. We are merging four dedicated functions into one function. That's called modularity. Is that right? Okay, now you understand. Yes. First off, alpha, yes, because we are dealing with alpha expansion. We are always consistent dealing with alpha expansion, alpha as input, okay? Yeah. So we can merge it into one, that is called modularity, all right? Yes. What's that? Union signs for what? For this one? The union sign is basically whenever alpha could be changed along the way. What we have here is we want to test the first of alpha if some symbol from the first of alpha. It means we can proceed normally. But if something went wrong, we also want to find, we have follow of n should be appear right here. We could safely back into the synchronizing, just a double ensuring that we are back into a synchronizing state with the some symbols we can proceed, okay? That is why we have a union. If we are dropping this part, it can be correct. It can be correct because simply we have the test of follow set right behind it. It means we are already back into synchronizing state. But here we are double making sure that we are literally in the synchronizing state and we can proceed it normally. Okay? This is double safety. And here, what we have here on this slide is another refinement. The caller of the procedure now bears the responsibility for computing and passing an appropriate follow set. For instance, if a procedure N is called from within another production codes, and the caller must determine which token can follow N according to the grammar. And those tokens form the follow set argument. This pattern makes the error handling modular. We have talked about modularity. Each non-terminals only know about its own grammar rule, and while the caller provides contextual knowledge about what may come next. So when combined, those checks prevents most cascading errors and lets the parser recover intelligently, even when input deviates from expected structure. So let's see how this works in an actual grammar. Suppose what we have here is the procedure factor is calling or is called from a term in a standard arithmetic grammar. And if you still remember, the rules we are dealing with is the term is T produces FT prime, meaning that after a factor, a multiplication symbol may appear. So therefore, when the term calls factor, it passes its own follow set united with the symbol and multiplier symbol. And because the factor can be followed either a multiplication or by what follows a term. And this contextual or this context-sensitive passing of follow sets allows each procedure to make or allows each procedure to make a precise recovery decision. If factor encounters an invalid tokens, it would just simply skip ahead until it finds either a multiply symbol or one of the term's legal followers. So then return the safe control safely back to its caller. This design just maintains the both correctness and the resilience in the recursive descendant parsing. So that's the only key takeaway. You don't have to memorize this one. What we are talking about error code. The big old idea is we want to produce all the errors to the user. That'll be it. And how we implement that is basically from the first set on follow set. How we do the double safety is first of alpha and union follow of something. That is double safety. Okay, that'll be it. That's the only key takeaway. And we are connecting all the theory back to the working recursive descendant code, which is on this slide. On the left, we have the term procedures calling F, as you can see here, and factor procedures, and the passing along is follow set merged by a multiply symbol. And this lets the F knows what exactly a valid token after a factor could be a multiplication symbol. That's what literally is talking about this. So on the right, what we have here is factor shows the first set and the follow set guide the control flow and the recovery. It begins by checking that the next token is either an identifier, or open parenthesis or left parenthesis. If it's left open parenthesis, it will expect a matching pairs by calling E. By calling E, that is the expression procedure with updated follow set. If the right parenthesis is missing, we are going to simply raise an error, and this error will be triggered. But the parser stays the synchronized using that follow set, even though we have no multiply symbol or let's say close parenthesis, we still can back into the synchronizing state. The same idea applies if the factor is identifier. If identifier here, and this structure just ensures that both correctness and parsing and resilient in error handling. That's the only key takeaway. You don't have to memorize how to implement. It's just out of scope of the entire class. You just understand conceptually what is exactly working here, why it is working in this state, okay? This slide just shows how the same principles appear in a real PL0 compiler, and the factor procedures check for the tokens begin with a valid factor. This belongs to a set of, let's say, its phase begin systems. That is literally talking about simply a first set of a factor. Then it also received about, which is this one, is called fsys. Fsys is a follow set. The follow set as a parameter inside a while loop, as you can see here. And the parser checks if the token is identifier or number or left parenthesis, as you can see. So for the identifier, it validates its presence in the symbol table. For numbers, it consumes the number. And for parenthesis, it is simply recursive calling expression, ensuring that enclosing or closing parenthesis exists. For after each block, we are going to test follow set. And it confirms the parser exists the procedure in a synchronized state. This method just provides a more clean and modular foundation for working compilers front end, okay? So what we are doing here is we are extending the factor and terms procedures with the code generation ability. That is exactly what homework 3 is doing with code generation, not only parsing, but code generation. So as you can see, what we have here, the term procedure is called factor and loops around multiplication or division operator. What we have here is we can go into generate OPR04, OPR05 based on the operator, and each operator triggers the generations. And on the right, factor now performs not just the syntax checking, but also emits the code. For constant, what we have here is loaded literals. And for variables, we're generating loading instructions. And for numbers, what we have here is still loading the literal, LIT. And if the symbol is some left parenthesis or it calls expression recursively, and each step uses the same error recovery pattern. So test the checking and test the check code's validity while the code is emission mirrors the semantic meaning of the input. So do you need to remember this one? Yes, you only need to remember one rule, is this design is demonstrating how parsing and code generation are woven together cleanly with a single pass. Okay, that's the only thing you need to remember. And to finish this lecture, this table will appear in your final exam. And this table is more valuable for you to understand what exactly the first set or what exactly the follow set to your grammar specifically, the block, the statement, condition, expression, term, and the factor, etc. And this table simply summarizes the first and the follow set for every non-terminal in PL0 grammar, and those sets are the backbone for both parser and error recovery systems. And again, back to the review, what is first set? First set identifies what tokens can begin each construct. For example, a statement can begin, may begin with identifier, call, begin, if, or while. That's basically what exactly the statement can begin with some kind of tokens. And follow set lists the tokens that can legally appear after each construct. For example, what we have here is period symbol, semicolon, and end for the statement that can legally appear after a statement. Also, those relationship makes the parser possible to basically making us possible to build a particular parsing tables and synchronized during recovery. So the same structure supports both correctness and graceful handling of syntax errors. But why we want to understand it is, but if you understand it correctly, and those sets will interact with the key to designing recursive descendant compilers or parsing, and that's both robust and easy to maintain. Okay, so after learning everything, why? Again, why we want to learn this? Why we want to start for first? Why we studying on follow? Why we studying about nullable? Why we studying about this error recovery? We have talked about at the very beginning of the lecture. A naive parser, what you are doing here in homework 3, even in your homework 4, still naive parser, one that stops at first syntax mistake is perfectly fine, It's perfectly correct in a formal sense. It refuses to process any invalid input. Normal, naive, but effective. But that behavior is simply terrible for the real users. Just imagine the compilers would help just simply stops on the first missing semicolon. You would have to fix that errors one at a time. It recompile it repeatedly, just waste of hours of work just for the compiling. And our error recovery, especially through a panic mode, it makes the parsing practical. It lets the compiler skip past a more formed fragment, resynchronized back to a safe boundary, for example, semicolon, braces, and continue checking the rest of the program so that we can produce a set of errors to the users. And synchronizing means what? It means we are restoring the parser's internal state so remaining tokens can still be interpreted correctly, still following the grammar. The only key takeaway from this entire lecture is that the parsing is not just about recognizing structures. It's about building a resilient system that can handle imperfections gracefully. And robust compiler not only finds what's wrong, but keeps going, providing useful feedback and maintaining stability throughout the entire analysis. That is the goal when we are building a parser, rather than something naive. Okay? So that's the end for this lecture. And what we have here is I am having a homework 3 demo that is telling you step by step how we're going to debug what is happening in the pseudocode, why we're doing that, and what do we have in the symbol table, what do we have in a token list, etc. Okay, that's the thing I think the most valuable class you could have before implementing homework 3. And what I'm going to ask you to do is grab your homework 3 instructions. You can pull up in your computer or cell phones that you can follow along. Go to Appendix F pseudocode so that you can follow precisely what exactly happening in this stage, what exactly happening in the next stage. So we are on the same page. You have instructions? No? Yes? Good. All right. So let's proceed. In this lecture, homework 3 step-by-step demo, you are seeing only one input file, that is this input file. Okay, so before we're dealing with the input file, we have to translate into tokens. That is exactly what Lex is doing. Tokens is being presented on this way. Each one is translated precisely var 29, x 2x, comma 16, y 2y, and semicolon 17. Each one is aligned perfectly. All right, just follow that. What we have on the next slide is basically telling you inside here is a token list. What is exactly the token we are following? And the blue block is telling you what is the current token is. And on top of that, we have the green block. It means it is symbol table. Okay, what kind of symbols we have inserted or initialized or declared in the symbol table? Here is the program. What we have here is the recursive calling structure. Who is calling whom? What is the function we are doing right now? Currently, we're dealing with function program. And here, the blue block is basically telling you what exactly the instruction we are generating right here. And here, at the very initial stage, we have generated nothing. So that is why we have empty. And what we are going to do is the current token input is 29. But once we coming back to the instruction here, so program and functions, that's the program we are dealing with. So program, the first thing is doing what? Calling the block. So as you can see here, we are calling the block. And how you can follow with the instruction, calling the block, and we're getting to the block. The first function or something we are going to do is constant declaration. Constant declaration, as you can see here, is basically telling you is constant decal. We are in the constant declarations. But as we know, the first token is var symbol. Is var symbol equal to constant? Nah. So we are going to skip entire if statement and basically given the control flow back to the constant declaration. So we are giving the control flow back to the block. And here we are going to continue our execution, which is var declaration. var decal it is, then based on the pseudocode, go to the var declarations. And we have a local variable called number of variables. That is 0, initialized as 0. Is the current token equal to var symbol? Yes, it is. So we are going to grab increment number of symbols and grab the next token. Grab the next token is 2. 2 is identifier symbol. It is identifier symbol, so it means we have no error. We have no error. Next one is we are going to grab the next token. We are going to find X from this symbol table. From this symbol, do we have a declared X in the symbol table? No. So it means this one is satisfied. So X is being checked. This not found in the symbol table. So no errors. We simply go to the next part, which is inserting that symbol into the symbol table. Inserting. So this is my implementation about the symbol table. Index 0 is reserved at what? What? Index 0 is initialized as what? Error. So whenever we go to the index 0, it means the symbol is not found. So that is the idea. So once we inserting, the index is 1 and the kind is 2. 2 means is a variable and name is X, directly grabbing from token list stored in the symbol table. Value Y0. Because a variable does not store any value. Okay, level 0. In your homework 3, we are not dealing with any complex structures. Therefore, we only have to deal with level of 0. Okay, and address y plus 2. Why is y plus 2? Going back to the pseudocode, number of vars is equal to what right now? 1. 1 plus 2. Why 1 plus 2? Let me ask you. 3 right now. Why 1 plus 2? Yes.
Would it happen to be because X is the third token here?
Not necessarily. Not necessarily. Yes. What's that? Yeah, go ahead. Is it 2 things before? It's coming back to our knowledge of homework 1. One activation record stores 3 necessary information. They are and what? And return value is PC. Static and dynamic and PC. 3 values. And what we have 3 values in the index in the activation record is 0, 1, 2. It means whatever additional local variables should be appear in 3, 4, 5, etc. Okay, so why we have 3? Why we have 2? Whenever we have additional variables, we are going to give it 3 and forward. Okay, so now we have the first instruction symbol is being inserted, and we simply grab the next token. That is 16. 16 means what? It's comma. It's comma, right? Comma. So we're checking if the token is equal to comma. Yes, it is. We simply go to the next symbol. That is 2. 2 is identifier. Is identifier? Okay, no problem. It's no error means. And we grab the next token. We are going to check if the Y initialized or declared before in the symbol table. No. Okay, well, no error. So we simply add the symbol into the symbol table to be 2. The kind is 2, still variable. Name is Y, value is 0, level is 0, and address, simply we have the variable of numbers to be 2 right now. 2 plus 2 is 4, so 2 plus 2, and initial mark is 0. Okay, good for now. And simply we grab the next token, which is then defined in this line. Grab the next token, that is 17. Is 17 equal to comma symbol? Nah. So we simply go to the next one is token is equal to semicolon. It is, so no error, no error. So we grab the next token. Grab the next token, that is 20, okay? 20, and we are going to return the number of variables and return this entire control flow back to block, okay? So now we're giving the control flow back to the block, and we are missing one, that is we are going to generate instruction for inc 05. What do we have recorded for the number of variables? 2. And we have defined all necessary bits in a single activation record is 3. 3 plus 2 is 5. Inc 05 means all the necessary information in this activation record is 5. Static link, dynamic, and PC, X and Y. 5. Okay? Now, go to your instruction, and what we have here is statement. We are going to call statement. Go to the statement, and we are having the statement, which is a huge chunk of a statement or switch statement. And what we have here is 20 is what? Is begin symbol, right? Begin symbol is telling you this is the function, or this is a part of what we are going to invoke. So begin symbol, and as you can see here, is invoking the begin. Begin, we simply grab next token. Next token is 32, and we are going to invoke the statement again. Going to invoke the statement, and what we have here, 32, is read symbol. This is the function we are invoking. And simply grab the next token. Next token is 2. We check if that token is identifier symbol. Yes, it is. Okay, no error. Then we are going to simply grab the next token, that is Y. Y from the symbol table. Have we defined before? Yes, we did. Which one is it? Oh, this one. Okay, index 2 is the one we are going to return back to the pseudocode. So inside the pseudocode, it is saying -1 is the error. But in my implementation, I'm going to modify it to be 0. If it is equal to 0, it means not found. Okay, that is my modification. Excuse me. That's my modification. If it's 0, it's going to give me an error. No, okay, so no error. We have index 2 actually. Then we're going to check its kind. A check kind is 2. 2 means it's a variable. No problem. We can assign some numbers to a variable. And some next one is we are going to grab next token. Next token is 17. Okay. Then we are going to emit read. What is the instruction for read? What? Yes? No, we are going to emit the instructions for read. Is that the one you are seeking for? System 02. That's read the instruction literally from your homework 1. And then we are going to emit store. Okay? Emitting store. Store 0, because 0 minus 0 is 0. So relatively speaking. And what is the current address for Y? Literally from the symbol table, 4. Okay? Grab that. Then we are going to return this control flow back to here. Okay? Return back to statement begin. And we are checking if the token equals to semicolon. Yes, it is. Then we are going to loop again. Grab the next token. Simply grab the next token, that is 2. And then simply we are invoking the statement again. Statement is the one we are dealing with. And the current one is identifier. So we are going to invoke this part. Okay, I think it is a perfect time to stop right here. And we are going to continue examples on Wednesday. And for whoever is attending on Zoom, thank you for coming and have a good day. I'm going to close that.